Dear students, I am happy to share you today the higher coordination numbers. Myself, Dr. Digna Varghese, coordination number 7. Coordination number 7 cannot be considered at all common. The relative instability of these coordination complexes can be attributed to the fact that the additional energy of the seventh bond is offset by increased ligand-ligand repulsion, weaker bonds, the generally reduced ligand field stabilization energy as a result of non-octahedral geometry. So these are the factors for the instability of the seventh coordination number complexes. Even though these are not very common, but seven coordination complexes is encountered for a few 3D complexes and many more 4D and 5D complexes where the larger central atom can accommodate more than 6 ligands. Geometries for coordination number 7 complexes. There are three geometries known. The first geometry is a pentagonal bipyramid geometry. That is, you can see from this picture, which is also found in the main group compound IF7 that you know. Here you can see a coordination number 7 complexes having the geometry a pentagonal bipyramid geometry. Okay. Here the molecular structure of the 7 coordinate complex of iron. The central atom is iron, which is joined to 213 dimethyl 369 12 18 pentaza bicyclol octadeca pentene, and there is two axial ligands, that is thiocyanate 1. The hydrogen atoms are omitted here for clarity. Okay, so it is a pentagonal bipyramid compound of iron having coordination number 7. Okay, second one is a capped octahedron. You can see its picture here. Here one of the ligand or the seventh ligand is added to the one of the triangular face of the capped octahedron. Such a compound you can see here the molecular structure for holmium complex, that is central atom is holmium and a water is the seventh ligand which is placed at the one of the triangular face of the capped octahedron. So it is a tris diphenyl propane diatomato aqua holmium 3. So the seventh ligand is water. Water is placed on the one of the triangular face of the capped octahedron. And the third geometry is a capped trigonal prism. You can see here the picture for capped trigonal prism. In this, the seventh ligand is placed one of the rectangular face of the capped trigonal prism. For example, you can see the heptafluoroneobiate ion. The central atom is niobium and the surrounding seventh ligands are fluoride ion. So these are the geometries of for coordination number 7, that is pentagonal bipyramid, capped octahedron, a capped trigonal prism. They are of comparable stability and easily interconvertible. A 7 coordination resembles 5 coordination in the similarity in energy of its various geometries. So 7 coordination complexes resembles 5 coordination complexes in the similarity in energy. Okay. A method to force 7 rather than 6 coordination on the lighter elements is to synthesize a ring of 5 donor atoms that they occupy the equatorial positions, leaving the axial positions free to accommodate 2 more ligands. Okay, this is a tip to prepare a complex with coordination number 7 for lighter elements. In order to synthesize such a compound, you have to synthesize a ring of 5 donor atoms. Then this can occupy or attach to a metal to form a 5 complexes, and this 5 donor species, okay, a ring donor, 5 donor atoms. Here you can see 5 nitrogen atoms that can attach to the metal atom. So in the metal atom there is 2 more valency to accommodate 2 more ligands. So we can easily synthesize a 7 coordination number complex. So this is a tip. And another examples of compound having coordination number 7, that is molybdenum CnR7 2 plus zirconium heptafluoride complex, tantalum triphenyl phosphine and tetrachloride complex, and here rhenium complex with the 6 chloride ions and oxide ions, that from the D block, and from the F block, that is uranium complex. Okay, so these are some examples of coordination number 7 complexes. Even though it is a rare coordination number, but it is some complexes exhibiting or coordination number 7 complexes are also known. Now I am going to discuss a type of 7 coordinate complex. It appears as though the 7th coordination that is formed by the forced by the geometry of the other 6 coordinating atoms. For example, you can see a series of metal complexes derived from the particular ligand py3 trend. Here the py3 trend is C5H4NCH double bond NCH2CH2 thrice N. The molecular structure of the ligand is shown here. You can see there are 7 nitrogens. One is 3 nitrogens are from the pyridine unit that you can see here, and other 3 nitrogens are imine nitrogens that also you can see here, and there is a 7th nitrogen that occupies at the top of the ligand. So there are total 7 number of nitrogen atoms that can donate electrons to the metal and form a complex. Here the metal atom for this particular complex is manganese, iron, cobalt, nickel, copper or zinc. Here you can see a structure of the molecular structure of the zinc 2 complex using py3 trend ligand. And here you can see the 3 pyridine nitrogen atoms that are coordinated to the zinc metal ion. Here the imine nitrogens are also coordinated to the metal ion. But you see here the 3 imine nitrogen atoms are more closer to the central metal atom zinc than the pyridine nitrogen atoms. And here the imine nitrogen atoms are at a 1 equilateral triangle and the 3 pyridine atoms are at the vertices of another equilateral triangle. Okay. So one could refer to this arrangement as an approximate octahedron. Here the 3 nitrogens and forming a 6 coordination to the with the metal atom and form an approximate octahedron. But since the metal ion is more closer to imine nitrogen than to the pyridine nitrogen, it is best to refer to it as a trigonal antiprism. By this, the 7th coordination number, that is the nitrogen, 7th nitrogen is coordinated to the metal atom through one of the rectangular face of the trigonal prism. Okay. So although both the geometrical and optical isomerism are in principle possible in 7 coordinate complexes, but no examples are known. But py3 trend complexes must be optically active. Now we are going to discuss the coordination number 8 complexes. Coordination number 8 cannot be regarded as a common. The number of known compounds has increased rapidly in recent years, so that it is now exceeded only by 4 and 6 coordination. Two factors are important in favoring 8 coordination. First one is the size of the metal cation. The ligands attached to these metals be relatively small and electronegative. The commonest ligating atoms are carbon, nitrogen, oxygen, and fluorine. The formation of 8 dative sigma bonds to a metal with a small and electronegative ligands. Second factor which are important in favoring 8 coordination is the oxidation state of the metal. A high formal oxidation state favoring 8 coordination. The formation of 8 dative sigma bonds to a metal in a low oxidation state. Please listen, in a low oxidation state would result in excess electron density on the metal. So, if electron density is higher on the metal, it does not require any additional ligand to form a stable complex. But the high formal oxidation state is high means its electron density is small. So it favoring 8 coordination from the by the electron acceptance from the 8 Lewis bases. Okay, so these two factors, the factor one is size of the metal cation, that is, and the second one is the formal oxidation state. The common oxidation states are thus +3 or greater, resulting in electron configurations with few remaining d electrons, such as d0, d1, d2. The size of the metal cation in order to accommodate 8 ligands, so it forms a stable 8 coordination complex. It must be the metals must be sufficiently large to accommodate 8 ligands without undue crowding. Okay, relatively few 8 coordinate complexes are known for the first transition series, that is 3D series. The largest number of this type of complex are found for the lanthanides and actinides. 8 coordination complexes are mainly found for the lanthanides and actinides. It is fairly common for zirconium, hafnium, niobium, tantalum, molybdenum, and tungsten. What about the geometry of coordination number 8 complexes? There are several coordination polyhedra available for 8 coordination. The first one is the cube. You can see the cube structure and its symmetry is OH. Second one is trigonal dodecahedron. You can see here the triangulated decahedron or dodecahedron having symmetry D2D and the square antiprism symmetry D4D. Both trigonal dodecahedron and the square antiprism may be considered to be the distortions of the simple cube, resulting in reduced ligand-ligand repulsions. So, this square antiprism and the dodecahedron is obtained by the ligand-ligand repulsion from the cube and forming a distortion so that these geometries are obtained, but these two are the most common geometries. From the valence bond point of view, the formation of both the dodecahedron and the square antiprism can arise from the sp3d4 hybridization. The cubic geometry, the most symmetrical arrangement is simple cubic. This is for UF8 3 minus Na3PF8 ET4N 4 times U NCS 8 times. Okay, these are some cubical arrangements for the complexes. Here you can see the UF8 3- structure, that is a cubic structure. Second one is square antiprism. This depicts a distortion in the cubic geometry which is adopted to minimize the repulsions between the anions, that is ligands. The common examples are TaF8 3- that you can see here. It is a square antiprism. Both the square is attached to the central metal atom. And ReF8 2- cesium uranium NCS8 and zirconium acetyl acetonato complex. These are square antiprismatic complexes. And the third one is dodecahedral geometry. This type of geometry is exhibited by complexes such as MoCN8 4- and zirconium OX4 4-. So these are the some examples of cubic, square antiprism, dodecahedral geometry having coordination number 8. Here you can see the energy level diagrams for 8 coordination. Here you can see the cube OH symmetry EG to T2G, and here the one square antiprismatic geometry having the level A1, E2, E3, and for the D2D, that is dodecahedral, having B1, A1, E, B2. These are obtained from their character table from the group theory. Now we are discussing the isomerism in coordination number 8 complexes. There are extensive possibilities for the formation of geometric and optical isomers in 8 coordinate complexes. Thus far, apparently only one pair has been completely characterized. Okay, the dig line, that is di-2-methoxyethyl ether. Its formula is OCH2CH2OCH3 that forms an adduct of samarium iodide. You can see its formula SMI2OCH2CH2OCH3 twice has been isolated in both cis and trans forms. The trans complex has a center of symmetry. You can see the trans compound samarium I2 compound. The stereo views of the structure of trans samarium complex, Digline complex. It has a center of symmetry. Thus, IMI and SMI angle is exactly 180 degree. Okay, and the molecule is bicapped, trigonal, antiprism. The cis isomer has the lower symmetry of a distorted dodecahedron with the IMI angles of 92 degree. Here you can see somewhat perpendicular. Okay, that is 92 degree. So it is a distorted dodecahedron geometry. Here the trans isomer is found to be a bicapped trigonal antiprism with a samarium I angle by triangle is about 180 degree. Higher coordination numbers. There are few structures known with coordination numbers larger than 8. The existence of coordination number 12 in some crystal lattices was mentioned. Larger atoms and ions, particularly those of the F block, tend to form complexes with high coordination numbers. That is, 9 coordination is particularly important in the F block. Coordination number 9, there is only one symmetrical arrangement known for this coordination number. This is derived from a trigonal prism by placing the 3 additional atoms outside the centers of the 3 vertical faces. Discrete 9 coordinate structures are known for complexes such as lanthanum H2O9 3+, neodymium H2O9 3+, and for the hydride complexes MH9 2-, where M is technetium or rhenium. Here you can see the molecular structure of the rhenium hydride complex, that is REH9 2-. The central atom is rhenium And here you can see three hydrogen atoms that are placed at the three vertical face sides of the trigonal prism. And here also you can see other three hydrogen atoms at the vertical side of the antiprism. Here the central metal atom, rhenium. So there is three hydrogen atoms here. The three hydrogen atoms. One is here, and the other one is here. You can see with double circled hydrogen atoms. These hydrogen atoms are placing the outside the centers of three vertical faces. Okay, so it forms a 9 coordination. These structures are formed by adding a rectangular faces of a trigonal prism. Okay, here you can see the rectangular faces of a trigonal prism. So three rectangular faces in which three additional hydrogen atoms are placed. No compounds are known with 10 or more distinct ligands. However, a few 10 coordinate chelate structures have been described. One possible structure is a double trigonal bipyramid with a bidentate nitrate or carbonate ions at each of the TPP sites. Here you can see there are double trigonal bipyramid structure, a pentanitrate of cerate 3 ion. Here the central atom is cerium, and here the nitrate ion is attached to the central atom in a bidentate fashion and forming a double trigonal bipyramid with the bidentate nitrate ion and forming a 10 coordinate complex. Another one is coordination numbers as high as 12 are also known with 6 bidentate nitrate ligands along the edges of a dodecahedron, but these complexes are of rare. Okay, here the cerium is the central metal atom and the nitrate is attached to the cerium through two oxygen atoms in a bidentate fashion. Here also you can see the same compound cerium NO3 minus. Here the 10 and 12 coordinations are encountered in complexes of the F block M3 plus ions. Okay, examples include cerium NO3 minus, which is formed in the reaction of cerium 4 salts with nitric acid. Okay, each NO3 minus ligand is bonded to the metal atom through or by two oxygen atoms and forming act as a nitrate ion in a bidentate fashion. An example of a 10 coordinate complex is other one thorium complex, that is THOX4 OH2 twice 4 minus OX is oxalate, in which each oxalate ion ligand provides two oxygen donor atoms. These high coordination numbers are rare with S, P, and D block ions. Thank you so much for your interest and attention.